Good morning, everyone. How's it going? Um, all right, so me and Shri are going to be talking to you about bqplot today. It's a plotting library in Python. But before I start, we have two versions of this talk that we give. One that's much flashier, and one that's more introductory. So just for a show of hands, how many people here have heard of bqplot or seen a demo? Okay, all right, fair enough. I will go through the introductory version then. Okay, so what is bqplot? So the way we describe it usually is that bqplot is an interactive plotting library for the Jupyter notebook. That means a lot of things that I'm going to explain soon enough. But it's an open source library that we developed while we were at Bloomberg. It's Apache licensed and on GitHub. And usually when I say this, people say, oh God, another plotting library. I have like 8 different APIs to memorize at this point. I haven't done a single line chart without Google since 2009. So yeah, that's fair. But in some sense, I think it represents the diversity of the Python ecosystem, that we have different tools for different use cases. So the question is then, why learn bqplot, or why Google how to do things in bqplot is the way I say it. And the way we usually describe it in non-PDF is with moving GIFs that say that with 19 lines of plotting code, you can usually do the entire demonstration of Hans Rosling's famous Wealth of Nations. And with 8 lines of plotting code, you can generate Nate Silver's famous election map. And all of this code is in Python and a full-fledged web application. So the reason that your bqplot can be more interactive than other libraries is because it's really built for the notebook, and the notebook is built in a web browser. So we can really leverage D3.js and all of the incredible work that's been done on the JavaScript side for data visualization. And the best part is we can bind that to Python functions. What that means is that your Python code can now serve like a JavaScript, like in the same way as JavaScript, modifying your visualization on the fly. And on top of that, we're built on top of the widgets ecosystem. And that means that any other library that's built on top of it, whether it's IPyVolume, the 3D plotting library Py3.js, the mapping library IPyLeaflet, they all play extremely well with us. So the bqplot team is mostly at Bloomberg. I'm at Amazon, and Sylvain is at Quantstack in Paris. We're on GitHub, and like any other open source project, we always welcome new contributors. Okay, let's go to the demo. Okay, so bqplot has 2 different APIs. One is a very matplotlib-esque API. Full screen. With the Mac, when you full screen, Chrome does funny things. So I usually avoid that, but I can zoom in. Oops, too much. bqplot has a matplotlib-esque API, and the reason I say that is because we try to emulate matplotlib as best as we can. In some senses, we avoid it if we think that the API in matplotlib was cumbersome. But so just like matplotlib, you can do plt.scatter with your x data and your y data, and you get a nice little scatter plot. The difference in bqplot in fairness to matplotlib now, I think the newest versions are similarly built, is that this is an entire interactive web application. So it has panning, zooming, everything that you would like, just directly when you plot, when you generate a plot. You can save the plot, refresh, do whatever you like. The big thing about bqplot is that it is really an interactive library. So when you declare the scatter, every trait, every attribute, every part of it is an interactive widget. That means even after you've generated the scatter, you can go back and change it. So if I do scatter.y and I change the data, you see it's the original plot that's going to change. And I can do that n number of times, and I don't have to redraw anything, actually. I can add animations, and that's going to give me something a bit funkier. So it's going to show me how the data is moving there. I can change the colors, I can change the shape of the scatter plot. But the most powerful thing for us comes if you have an arbitrary function, let's say foo, and we want it to do something. Whenever someone interacts with the plot, we can define foo, and we can say, for the scatter, observe foo whenever the y value is changed. Let's let the user move the scatter values. So if we go back here, we take this point and we move it, that's going to call our function directly. There was no JavaScript involved in this. All of the JavaScript has been taken care of. Yeah, it's been done by us, rather. Yeah, not that I want to recall it, but if you see, it also passes all of this data to you. Tells you what was changed, the old values and the new values, so you can use that to really customize what kind of reaction you have anytime the user interacts with your plot in a specific way. How do we use that? So we try to do a lot of things with it. We generate funky little maps sometimes. Other times basically for us, so in 8 lines, 10 lines of Python code, this is a county map depicting the winners for each year. And you can make the tooltip depict any aspect of the data that you pass to your map. So in this case, I do the color. So you can see at each point, you can zoom in, you can say, inspect the counties. And all of this is done in Python, taking the data, creating a tooltip, and then creating, just doing plt.geo, which creates a map plot. So that's kind of how we use it. We give ourselves kind of free interactivity. The cool thing is the tooltips can be any sort of widget. So if I define another figure, let's say the world map, I can put a tooltip in it that shows a line chart. So you could have the GDP for each country if you like. When you hover on it, that's a pretty good exercise that we usually leave to the audience. Is that change the line chart on depending on which country you're hovering over. We also have the notion of selections. So you can click on a point and select it, and that's going to change the selected attribute of plot. Usually you don't see anything, so the best way is to change the style for the selected and unselected points. And you can go and select multiple ones if you like, and you can then let the user, and you can define a custom reaction based on which ones the user has selected. This works for countries, line charts, bars. It's kind of a uniform API. So one thing I did mention was that bqplot interacts really well with the rest of the widget framework. So how do you use that? So imagine if you had something like linear regression. You fit a line to the square errors. It's a bit like dropping a line vertically from that from each blue point onto the red line. But you want to see how your outliers affect particularly the slope of this model. Let's say what you could do is you could take this point and move it, and on each move you could refit the regression line and see how the regression line changes because of a single outlier. And as you can see, it's kind of badly affected by it. It's a well-known problem with linear regression. So you could try different methods that correct for this, regularization, etc. What you'd see is that, so it kind of gives you a convenient way to have all of your numerical code, which is already in Python, mixed with interactive visualization without having to write any JavaScript or anything like that. Another cool example that we always have is a polynomial regression. So this, instead of fitting a line, we can fit a second order polynomial or a third order, and gradually as we increase, we start overfitting and we start having weird behaviors. So that's always a fun visualization. So another cool one that okay, so all right, I'm going to give it to you at 11, so I go quicker through the thing. Okay, so one cool visualization that we have is related to the MNIST dataset, and it's kind of the baby steps of deep learning. You have handwritten digits, and you classify them. So imagine if you were working with this dataset. The first thing you'd like to do is to look at your data, so you can go through and look at all the different plots. You see that these, some are pretty funky and distorted, and I think that's how the data set was generated. You can also use a projection algorithm like tsne to take this very high dimensional image. It lives on a 784 dimensions or something like that, and project it down onto 2 dimensions. So what that means is that you can have a nice little scatter plot which shows you where all the points lie, and you can try to identify patterns within those points. The issue with that is that actually what happens is you see distinct clusters, but it's pretty hard to see what this anomaly is without going and looking back. So one thing you could do is you could put the actual picture as a tooltip and go and see which things are not really mixing well. And you kind of get an intuition that why some of them would not mix well. The other thing you could do is you could say, okay, but now I want to kind of separate them out so that I can actually classify them. One of the famous ways of doing that are convolutional neural networks. So here what we do is we take a pretty simple Linnet-like architecture and we look at the last dense layer. So the last layer before we classify anything. And we look at the representation that it's learned. And if that representation isn't clean, probably your model is not going to do very well. So what we can do is we can take the output of this intermediate layer, perform a tsne on it, and then see what kind of representation the second last layer of the connet has learned. And as you can see, it's kind of very separable, much cleaner, much nice. You could imagine why this would in particular work really well, and I think its accuracy was something like 98% on the validation set. So it does work really well. But you see some of the points are kind of strangely classified. So say this one. So you can go there and say, okay, what happened there? The actual was 1 and we predicted 3. So let's refeed this data point to the network and let's see if it adjusts its parameters in order to learn it. And you see, yep, within a single epoch, it did that. So now hopefully it got it right. Yep. And so you can go and inspect your data and essentially see where exactly you're going wrong. It's a bit manual, but if you're really facing problems with a certain class, it can be helpful. And then you can regenerate your tsne plot. And what in general you see is that you still see some points, but that point that you just trained will probably move back within its little cluster. The other thing you could do if you want to interpret it is look at the kernels for the first layer, see these little Gabor-like things, and you can really inspect them. The bqplot allows these kind of nice layouts just like matplotlib. Yeah, that helps us understand where exactly we should be fixing our nets, how exactly we should be tweaking our architectures. It's one way we use interactivity to kind of modify our workflows. Shri's going to show you some other visualizations that are actually a lot more fun, so I'm going to leave him to that so I can see them too.
Thanks, Dhruv. So I have like 10-15 more minutes, so I'll try to go over these relatively fast. So yeah, like carrying on with the neural net and deep learning tools and visualizations that we have. So here we are looking at the data set which is for predicting the defaults of individual customers. So yeah, so this is like the very famous Kaggle data set. It is called Give Me Some Credit. And so what we have here is we have some. So first we are trying to monitor how the training and test accuracy of our model evolves over time. So on the x-axis we have the epoch, and on the y-axis we have the AUC, the metric that we are looking at. And yeah, so here we can interactively see how the train and test error is evolving, and depending on how much of a gap we see between the train and the test, we can add more regularization to our model or add more capacity, and so we can interactively proceed based on what we see. And so, but this is like a very aggregate level analysis. We ideally want to get more deeper into the network and try to understand exactly what is going on. So I'm sorry, this is just taking a little bit of time. It should be done should be done pretty soon. I have 15 epochs. So in the meanwhile, while this is getting done, I'll just go over to a different example. So this is the very famous Wealth of Nations example, which many of you would have seen. So it was done by Hans Rosling, in which we are representing the GDP per capita and the life expectancy of the different countries. So I'll just quickly show you what we have. And yeah, so I'll just zoom out a bit. Okay. So what we have here is, on the y-axis we have the life expectancy, and on the x-axis we have the income per capita, and each bubble here represents a country with the size being proportional to the population. So this is a very famous visualization which many of you have seen. So we can go through the data like as time evolves by like linking it with the IPyWidget slider. So we do see that, yeah, on the whole, we are getting better in the sense that we would ideally want all the countries to go to the top right corner. And so it's very easy to add an animation. So here we use the IPyWidget's play button. So yeah, so it's very easy, like entirely in Python, you can add this animation where you can see how each country is moving over time. And then you can take that, you can like use the slider. And so to add a little bit more to the traditional visualization, we added a tooltip. So you can hover over any country and see the entire path that it has traced over time. So we do see for many of the countries that there is like this dip near World War I and World War II, where the life expectancy especially dropped quite a bit. But yeah, so this allows you to like understand your data a lot more easily and try to analyze it very easily. So yeah, now that this guy is done, so yeah, like we do see that, going back to the neural network example, we do see that we are increasing the training error, the training accuracy is increasing, but the test is slightly decreasing. So we may be overfitting a bit. But to understand what the network is doing, we have a representation of the graph, and we can see different attributes of the network by just hovering on. So what we are seeing here is the tooltip for the different nodes. So I'll just scroll a bit. And so here you can also see that on the right we have the incoming nodes colored according to the color of the bar chart. So we can see if all of the layers are being used, or if it is like super sensitive to a few of the layers. And you can also have, because all of these can be computed using Gluon here and most of the other neural network training packages that we have. So here we can also look at the gradients, and we can see how the gradients are evolving over time, and we can get a much better understanding of what the neural network is actually learning. And then we can try to understand like how to tune it and analyze it better. So next, what do we have? So since I work at Bloomberg, we are a financial data company, I have to, so this is like a pretty good financial example that we have. So all of you have heard that in crises, like all of the market becomes a lot more correlated than it usually is. But so you can like test this by looking at the correlation matrix in crisis situations. So here what we have on the left is the price series of the Dow Jones, and on the right we have the 30 stocks correlation matrix. So now we want to see how it changes over time. So in bqplot we add what is called a selector, and so here so this selector actually selects a subset of the time period, and by going down we narrow, by moving up and down we change the width of the interval, and then by moving across we can change the time period. So we can focus on a crisis situation and see how it actually affects. And we do see that when there is like a huge market drop in like mid 2015, the market, all of the stocks do become a lot more correlated. And so, as I don't remember who exactly said this, but there was this saying that the point of data is to get insight. And with bqplot, what we try to do is to provide you tools and ability to build visualizations which allow you to gather insight very quickly from your data. And I have a couple of more things to show. So yeah, this, as you know, like most of the mobile companies have like huge patent infringement and lawsuits going on. So this is a representation in Thomson Reuters website of like which mobile company is suing whom. So you can see that pretty much everybody is suing everybody else. But what you see here is I think this visualization is not very clear. You get a global picture, but then there are like too many lines and you don't really understand what is going on like at a very big picture. So then Mike Bostock has this visualization which he did using the D3 force layout. So here you can see, so if you want to look at say just Google, you can see that they're just being sued by Oracle, but then Apple is like in the middle of this whole big thing. So next we try to create this using bqplot using just so here this is just an import, and this is like the dictionary of all the data that we have, and using the graph mark we can recreate this. But then yeah, we have to add more interactivity so that you can easily understand your data. So now if you hover on Apple, you see that only the links which are connected to Apple are highlighted, and then you can easily understand for each company what is going on rather than looking at this, which is like slightly horrible. And so next, so oh yeah, it's already open. Sorry. So next we have an example in neuroscience. So this is what is called magnetoencephalography. So what it tries to, so in the human brain, when you see something, there are electrical spikes or signals in response to the stimuli that you see, and this MEG for short, this tries to measure the magnetic field generated by those electric spikes, and then tries to understand which part of the brain is responding to different stimuli. So here we take this unsuspecting guy, put this inverted R2D2 on him, and using that we get, so we can measure like what is the response generated by different stimuli in different parts of his brain. So what we have here is essentially a helmet which is recording the response of different parts of the brain. And so this is a 2D projection of the helmet seen from above. So the front part is the nose of the person, and this is the left of his head, and this is the right of his head. So the color represents the spatial location of the different electrodes. Now we try to see like how the brain responds to different stimuli and what parts of the brain are activated. So this is the entire recordings of the MEG over just 500 milliseconds. So we do see that there are like two big spikes where there was some response to stimuli, but like for the rest of the time it is like pretty flat. So the color corresponds to the area of the brain from which the stimuli came. So now, so we can try to go to the two spikes and try to understand like which part of the brain is being activated in each of them. So we see that for the first spike, like most of the activation is coming from the right side of the brain and the left side and the right side of the brain, and also from the back, but not much from the front. And we can also identify what is happening with the right spike. So we can also see that for the second spike that we have, the activation is kind of similar. It's more or less like the sides of the brain which are mainly activated, and then mostly the back. But as Dhruv said, we can easily link this with most of the other IPy widget based frameworks. So now we have, sorry, yeah, I'm not able to zoom on this. Sorry, I'm really bad with the Mac. I don't use a Mac. Yeah. No, it's not happening. Can you try? Yeah.
Oh no, that's how big you made it actually. Yeah, that's kind of how big you made it.
Okay.
You can rerun it and see if it gives you better size, but oh yeah, no.
Can you try to zoom? Yeah.
There you go.
Okay. Thanks. So yeah, you can now. This is like a 3D representation of the helmet. So you and then you can see like on different times what is the different parts of the brain which is activated, so that you can get like a good understanding of like you can easily understand your data. You can see where the signal is coming from, and then try to ask the right questions and quickly do your analysis. So yeah, that is pretty much all that we have for now. We have like 5 minutes. So yeah, if you have any questions, then we're happy to take them.
Can you explain like what technologies like bqplot is based off of, and also like how it performs like with larger data?
Sure. So like we are based on the IPy widgets framework. So on the Python and the JavaScript side, and for the plotting, we are mainly using D3.js. So we've written like our own abstractions on D3.js so that it represents the kind of top level classes that we want to expose. And for performance, so like if you have a lot of data, since this is like we render most of the marks in SVG, we do see some slight performance hits, but then you can like always overcome that with basically using some kind of data decimation algorithms, so that you like intelligently subsample your data and then only plot that. And then we can have like interactive zooming, and then once you zoom into a part, then we can render that data in greater detail. And so yeah.
And typically when you have large amounts of data, you don't really see anything. So we try to have simple things that you can do to just have a quick visual of it, and then kind of dive deep into it and have interactivity for specific subsets of it, I would say.
Time for one more question.
With the new Jupyter Labs supporting Vega Lite spec, how does that relate to bqplot in terms of visualization?
Oh, so we are so bqplot works in Jupyter Lab with the latest version of 0.27.1, and yeah, so like it's almost the same as how you would write and render as in the normal Jupyter notebook.
And yeah, on top of that, because we're based on the widgets, we can have, apart from the custom extensions, we can have different other types of extensions, like we can mirror outputs. So you could create full-scale kind of visualizations that are being controlled by a Python notebook and that are being displayed separately. So in the case of the training monitor, you could be looking at your code, inspecting your data in a notebook, but you could mirror the output in a separate tab in Jupyter Lab, and then monitor the the training and loss history curves. You can monitor the gradients. You can do things like that. In general, we've seen that's pretty hard with Vega Lite. I mean, it's not that easy. We're really built for scientific computation, I'd say, because we're scientists who built this for ourselves. So using it, we see that the things that we wanted to support in Jupyter Lab tend to make it easier to do scientific things.
All right, thank you very much, everybody. We have another session.